One of our last special cases for stress to look at is going to be in something called thin-walled pressure vessels. And these are really very common out in industry or out in the world. You may, if you're ever, driving through more rural areas, you may see these kind of big cylindrical tanks sitting around, or you may see water towers, things that may look like this. These are pressure vessels, and they often are in this kind of cylindrical form. Sometimes you'll see them in a spherical form. Those are usually a little more difficult to fabricate, so you don't see them as commonly. You often see them in this kind of cylindrical way. Here's a spherical one. Here's another cylindrical one. Sometimes they have more spherical end caps. But it's super common to see these just out in the world or when you're working in industry. And they're usually holding some kind of pressurized gas or liquid. So like when I worked at a water treatment plant, we had big cylindrical tanks like this in a room that held our liquefied chlorine, right? It was held under pressure so that the chlorine wouldn't turn into a gas. It stayed in liquid form and then could be added in small doses to sanitize the water. So you'll see these very commonly, at different plants and for different scenarios, different applications, but they do pop up. And so we'll talk about them as kind of a special stress case. So just a couple things on this is that the way we defined this thin-walled lets us kind of take some shortcuts when we're calculating this stress. But to be a thin-walled vessel, you need to have a radius to wall thickness ratio. So radius to wall thickness ratio, or R over T. We want that ratio to be greater than or equal to 10. So that the radius is 10 times larger, at least 10 times larger than the thickness of the shell itself, right? Of that pressure vessel. And then the other thing that we assume is we're going to assume that there's constant stress from that internal pressure. There we go. Yeah. So we're going to be able to calculate the stress that's actually on these walls, on the walls of these spherical or cylindrical vessels, due to the pressure of the gas or liquid or whatever substance that is pressurized on the inside. So here we've got a cylindrical one, which sometimes you might see like pipes and things also may be considered like a thin-walled pressure vessel. Lots and lots of applications for this. But we have two cases that we'll look at here. We'll look at both the cylindrical case and the spherical case. So here's our cylinder. Cylindrical. And this one is spherical. Spherical. There we go. Spherical. And essentially the way we calculate these is if you imagine like cutting through each of these vessels. So I'll start with the spherical one here. If I imagine cutting through him, right, and then he's kind of open in this little like half dome shape, and there's his thin wall we can kind of see there. Essentially what we're seeing is we're gonna see stress coming out around this loop here. So the way that we define the stress equation for a thin-walled pressure vessel that is spherical is going to be the normal stress is the pressure of whatever's inside. So whatever pressure that's causing on the walls of the sphere. So the pressure, P, this is a lowercase p, pressure P times the radius of the inside of the vessel over 2 times the wall thickness. So your sigma is your stress. Your P is your internal pressure. And that usually has the same units as the stress, KSI, PSI, pascals, whatever stress units you're using, it'll have the same units for pressure. And then your R and your T should have the same units as well. They should both be distance units, right? Because R is your radius of inside of vessel, inside of sphere, inside of the vessel there. And then T is the wall thickness. Whoops, wall thickness. So here's your, I go from the center here, this is the radius. This right here, that would be T, that would be my wall thickness. And then P would be the pressure caused by whatever happening inside. Right, so whatever is happening inside of that vessel is going to be the pressure value usually given to you, or the max pressure value, so one of those things, to calculate those stresses. So not too bad, right? A fairly straightforward equation that is a little bit different when we have a cylindrical vessel. So this is our equation for a sphere. But let's take a look at this cylindrical vessel a little more. Right, when we cut through this cylindrical vessel, there are two ways we can cut through it, right? It only makes sense to cut through a sphere in one way down the middle, right? It doesn't matter if you slice it this way or this way or this way. You're still going to end up with this general cross-section that we see next to it. But we have two ways that we can slice through the cylinder, right? So we can slice through the cylinder where we take a chunk that looks like a semicircle. Right, so if I kind of take like a chunk like this, kind of oversized chunk, but a chunk. So I can take a chunk that looks like this, or I can take a chunk that's more similar looking to this sphere, where I have a chunk like, all right, my cylinder goes this way, and I'm cutting through it, and I see this end of it. Right, so I can kind of see the insides, imagining if I cut through this way versus if I cut through this way. You know, a little bit different view of my cylinder, which gives us actually two different pressure equations, two different stress equations that we can apply. So if I cut through it this way, this left-hand side way, I'm cutting through the circumference, right? So I'm like cutting a little, like a semicircle wedge out of it, where I'm looking at the stress, the force that's being experienced in this section here, right? Through the circumference of this cylinder. So this is what we call circumferential. Circumferential, as in, you know, referencing the circumference. Circumferential, or the much easier to say, hoop stress. You can say circumferential stress or hoop stress is what we see in this diagram on our left here. And the way we define this stress value is quite similar to our equation that we derived up here for our spherical vessel, but it does not have the 2t term on the bottom. So for our circumferential stress, and I'm going to call this stress 1 since there are two stresses that we can see here. For stress 1, we're going to have the pressure times the internal radius over the thickness of the vessel, just the thickness of the vessel. So again, very similar to that spherical equation, there's not a 2 on the bottom. Now for our other case, our stress is coming out much like it did in the spherical case, where we cut the sphere in half and we were looking at the full circle cross-section, and we could see all of the force, all of the stress coming out of this. This is what we would call for the cylinder longitudinal stress. Longitudinal stress. So the longitudinal stress, because it goes along the long ways of the cylinder. Goes along in line with the longitudinal axis of the cylinder. And even easier than our first equation, our second stress equation is actually the exact same. It is the exact same as the spherical equation. So that makes it not too bad, right? There's only one difference that you need to know between the cylindrical or a spherical vessel, and that's that the cylindrical vessel has this circumferential hoop stress that is twice as much as the spherical or longitudinal stress in a cylinder. So similar equations, but fairly simple in application. Let's take a look at a quick example. So in this example, we have a cylindrical pressure vessel with an inner diameter of 4 feet and a wall thickness of 1/2 inch. And it asks us to determine the maximum internal pressure it can sustain if the allowable normal stress is 20 ksi. And then it asks what's the max internal pressure that a similar spherical vessel can sustain. Right, so we're looking for the maximum pressure that it can handle, a cylindrical vessel. So a cylindrical vessel, if we'll recall, it has those two stresses, right? It has the hoop stress, or the circumferential stress, which is our sigma, our normal stress, equals pressure times radius over thickness, wall thickness. And then we have that longitudinal stress, given by pressure times radius over 2 times wall thickness. So before we even calculate anything, which one of these is going to be the limiting factor? The equations are so similar, we can know just by looking at this which one will be the limiting factor in our design, right, for this maximum pressure situation. So for our maximum pressure, it's going to be whichever one of these equations gives us the smallest acceptable pressure, right? The smallest acceptable pressure, that is the limiting factor. It's the highest we can go. We can only go up to the smallest value. So we already know that it's going to be from our hoop stress equation, right? Because if we rearrange these to solve for pressure, we're going to get our pressure is the stress times the thickness over the radius, and this other one, pressure, is 2 stress times thickness over the radius, right? So this pressure is going to be twice as large as the pressure that we get from the hoop stress, which means it's going to be bigger than what we want. We're trying to find our limiting factor. We're trying to find that smallest acceptable pressure. So it's going to be given to us by this hoop stress equation, so we don't even need to calculate this other equation. We can just leave them alone. We already know maximum internal pressure is going to be determined by this equation. So we've rearranged it to solve for pressure, so we'll just input in everything that they gave us, right? They gave us the allowable stress of 20 ksi. So 20 ksi times the wall thickness was 1/2 inch. Over the radius, and that's the inner radius here, inner radius of our vessel. They gave us an inner diameter of 4 feet, so that would make our radius 2 feet, or 24 inches. 24 inches is what I'll put in there. And I get a pressure, when I plug that into a calculator, of 0.417 ksi, or I'll go ahead and convert that, 417 psi. Right, so that's the maximum pressure that it can handle in this cylindrical vessel. The pressure of the actual gas or liquid or whatever item we put inside of that vessel, the max pressure we can load it up to is 417 psi. Otherwise, we'll overload it and blow out the side, when we don't want that. We do not want all of that gas or liquid or whatever escaping. We want it to stay in the pressure vessel. So we will not load it more than that 417 psi. But our second question here is, what's the max internal pressure for a similar spherical vessel? Now our spherical vessel, for a sphere, that also uses our PR over 2T equation. So we know pressure is 2 sigma T over R. If we solve for this pressure, using the same values, right, 20 KSI, thickness of a 1/2 inch, same radius, just assuming that it was a sphere instead of a cylinder. 24 inches. Assuming it was a sphere instead of a cylinder, we would get double this value, right? We could have twice as much pressure in a cylinder than we could, in a sphere than we could in a cylinder, right? We could pump that up to 833 psi rather than be limited at 417 if we had a spherical vessel. Right, so a sphere would be a lot better, really. If we wanted to meet these same size constraints, we would want to put it into a sphere so we get a higher pressure. But spheres are more difficult to fabricate, right? It's a little bit harder to make a sphere than it is to make a cylinder. So you'll often find that people will accept this lower pressure value because you can make a larger cylinder. You can make it's a little bit simpler to go through the fabrication process and a little bit cheaper most times to get a cylinder than to get a sphere, even though the sphere would hold more. So these you'll see come up occasionally. These are just something to be aware of as we move on in this class.